Hi everybody, it's my pleasure today to tell you more about MuZero, our latest algorithm that connects the benefit of tree search with MCTS and a learned model. First, I want to cover the benefits of search and how Monte Carlo tree search works, and then connect this to how we can learn a model of the environment and then use it to plan with the search. So let's start at the beginning. Of course, the ancient board game of Go. This is how our story began with AlphaGo. And there our challenge really was this very ancient game with a very large action space. So many possibilities, too many to exhaustively tackle them with a normal heuristic-based search. So we tried to use neural networks to help the search. The first network that we came up with was the value network. It's equivalent to some intuitive estimate of how well am I doing in this position. And with such a network, we can really cut down on the depth of the tree. We don't need to search until the end of the game. We can only look ahead a few moves and then rely on the evaluation of our network to see how well we are doing. Next, we combine this with a second network, the prior or policy network. This network gives us an initial estimate of which actions are most likely to be the best action in this situation. Which, as a human looking at a board, at a game, what would we intuitively do? And again, this allows us to massively prune the tree. Now we can reduce the breadth of the tree. We can start by only looking at the most promising variations in our search tree. Together, these two networks allow us to search the most plausible, the best possibilities first, a very effective combination. Now, of course, we have to still somehow choose which positions to evaluate. How do we combine these estimates from the value and the policy network? And this is where Monte Carlo tree search comes into play. On the one hand, we want to evaluate many interesting positions, many interesting actions. On the other hand, we want to aggregate all of this information into one good estimate that we can use to choose the best action. So we can start with our schematic search tree. Here, the top, that would represent the root of the tree, the current position in the game, the current position in the environment. The lines, the edges, are the possible actions connecting one state to the next state. And as we follow some action sequence, we can arrive at a state in the future. So starting at this root node, we want at every level to select the most plausible action, the most plausible node, leading us down the tree. And here we want to trade off. We want to, on the one hand, explore very promising actions, most likely to lead us to a win. But on the other hand, we also want to explore parts of the tree that we know very little about. We want to trade off exploration and exploitation. And the formula we use for this, PUCB, at its very essence, gives us a way of combining the estimates of our two networks, of the value and of the policy network. And we can scale this with some constant that allows us to trade off exploration as we search more and more, and as we acquire more information about the tree. And the exact shape of this constant is not as important as the general idea. The more visits we have, the more evaluations we have, the less weight we want to give to our policy, and the more weight we want to give to our aggregated value estimate. Now we can apply this formula recursively down the tree, always selecting the node, the edge with the maximum UCB value. And we can repeat this until we reach a leaf node, a node that has not yet been evaluated, that does not yet have any children. And now we can evaluate this node with our networks to get new policy and value estimates. And then we can propagate them back up the tree. So we propagated the value estimate up to its parents. So every parent, every node in the tree can keep the average over all its children, the whole subtree. And this ensures that our value estimates become more and more accurate as we search longer, as we perform more evaluations. This is the algorithm that we used in our first Nature paper, AlphaGo, which we also used in South Korea to play against the legendary Lee Sedol. And AlphaGo became the first Go program to beat professional human Go players. That was a very exciting match, but that's a story for another time. As a next step, we wanted to take the algorithm further. So in AlphaGo, we had still trained those neural networks, initially based on human Go games in supervised training. Now in AlphaGo 0, we managed to completely remove the need for this human knowledge. So we could train AlphaGo completely from scratch, starting from random play only against itself. Next, we also removed the restriction to Go and generalized the algorithm to other board games, to chess and shogi in this case, the most widely played. We could also rely on a lot of advances in machine learning accelerators at this time, which really made our work very exciting and helped us a lot. Here is a rack of TPUs in Google's data centers. This is when we published the AlphaZero algorithm. And I think even though in chess, programs were already playing at a superhuman level for a long time, surprisingly, at least for me as not a good chess player, a lot of people were still very excited because AlphaZero actually played a lot more human-like moves. Funnily neat, because even though it had never been trained on any human data, but possibly because of the way it learned for itself, playing against itself. So we found this again and again in different games. Quite interesting. Now, finally, we wanted to take the next step in generality. We wanted to jump from board games, from games with very well and clearly defined rules, to any arbitrary domain where we might only be able to interact with the domain, but might not directly have access to the rules of the environment. As would be the case, for most video games, as would be the case for any general real-world problem. And as our test bed, we chose Atari because this has been a long-standing challenge domain for reinforcement learning with very strong baselines and a lot of published results. And our approach was minimalistic, as always. We wanted to only predict what we really needed for planning, what we really needed for our tree search. The policy and value estimates, and also rewards for games with intermediate rewards. So now let's have a look at how the learned model comes into this. So how do we actually plan with a learned model? What does it even mean to have a learned model? What components would we need to plan? So let's start at the beginning, right? We are in some state of the game, here schematically represented by a little Go board. And of course we cannot, roll forward a simulator. We don't have access to a simulator. So instead, as a first step, we need to map this observation using some representation function h into our abstract embedding space. We call it S here for states. And if we have this embedding space, then we can try to plan in this embedding space. On the one hand, we can make predictions based on the current state, and we can predict the policy and the value estimate. But of course, given some action, we can also estimate what would be the next state that we could end up in. We can have a dynamics function g that can map from one state into its successor state given the action that takes us there. And this will also predict any reward that we would observe along the way. And just using these three functions that can of course be represented by a neural network, we can roll forward and we can build our search tree, just like we saw in the previous section. Now, you might ask, why do we want to use planning? Are there not a lot of other algorithms? Well, our motivation for using planning specifically was that we can really view this as a policy and value improvement operator. Other algorithms, for example, policy gradient or Q-learning, there might be a one-step look ahead, given the current state, estimate the values of all the actions, and then do an improvement step with respect to those values. Similarly, here we can look ahead many steps. We can build a whole look ahead tree over actions, and then we can use that whole tree to improve our estimates. And in our experience, this has been highly effective. So let's talk a little bit more about this. Now that we have the search procedure, of course, we can also repeatedly apply it, generate some search statistics. We can select an action from those search statistics proportional to the visit counts in the search. We can apply the action to the environment, and then we can repeatedly apply this procedure until we've played the whole game. We've generated the whole trajectory of experience. There are two important points here in how we run the search and how we select our action. First, when we run a search during training, we always add Dirichlet exploration noise at the root of the tree. And this ensures that eventually the search will be able to explore all actions, even if they initially started with a very low prior. And the reason why we chose Dirichlet noise is because in expectation, this is a very peaky form of noise that on average, it will boost 1 or 2, maybe 3 random actions to a high enough prior that they will be selected, and it will not affect all other actions. Because of course we don't want to distort our prior too much, because it is what we rely on for an effective search. The other component comes into play after we've run our search. It is how we select the actions based on the visit counts. We can view those visit counts as a probability distribution by normalizing it, and then we can apply a temperature to control how uniform to greedy we want to sample. And we can use this to ensure that our games are not deterministic and to ensure that we explore a variety of trajectories and positions in the state space. And then, now that we have these trajectories, they contain all the information that we need to train our network. You can see we have policy estimates, we have value estimates, we have rewards that we have observed. So now we can combine this with the components of the learned model, and we can actually come up with a way of training this. You can see here, we've taken the trajectory, a trajectory that we've just generated, and then we can unroll our learned model alongside this trajectory. Again, we can use the representation function to map from the observation to some embedding space. We can use the dynamics function to roll forward from one state to the next. And we can use the prediction function to make our policy and value predictions. Importantly, observe that we do not use any future observations at all. We only use the history of observations in our representation functions. So when we align this trajectory, you can see actually it aligns very well with the search data that we generated during self-play, during acting, which we of course stored for later training. For the policy, we can simply train by distilling the visit counts of the search. It's a simple cross-entropy loss between the policy and the visit targets. Similarly, the reward can be a prediction of the actual real reward observed. And for the value, we can use n-step bootstrapping. So we can build the discounted sum of future rewards for n steps, and then we bootstrap from the value estimate at this point. And at every time step, we multiply by some discount. In Atari, we use the standard discount of 0.997 as previous work. And in board games, we don't discount at all. In fact, in board games, there's only a single reward, final win or loss result. Now, here you have the whole of MuZero at a single glance. On the left, how we use the learned model to build a search tree. On the right, how we then use the search to generate trajectories, and how we can train our learned model from those trajectories. Now let's look at a few results. Let's look at how well this actually all works in practice. First, of course, we applied this to the classical board games, chess, shogi, and Go, the same games that we had used in AlphaZero. The reason for this is that we wanted to verify that the learned model can plan just as well as AlphaZero using the real simulator. And indeed, you can see here the horizontal orange lines represent the performance of AlphaZero. The blue training curves show how MuZero can reach the same playing strength at the end of training. For Atari, which we chose, as I mentioned before already, because it's a very standard reinforcement learning domain, we compared against the strongest baseline we could find. The horizontal orange lines show the mean and the median performance of R2D2 on 57 games. And the blue lines show the performance of MuZero over training. And again, you can see that it can achieve and even exceed the performance of R2D2. Here you can also see the more detailed results for Atari in a table comparing to previous algorithms. And you can also see that we actually used a comparable or even smaller amount of data, of training data. This is important because in Atari, playing strength and mean reward strongly correlates with how much data an algorithm can be trained on. Now, we've seen that we can get very good results from our learned model, but can we also use it to maybe learn a bit more efficiently? You know, you might argue 20 billion frames is an awful lot of frames. Certainly a human does not play this many frames of Atari. Maybe we can use our learned model to approach this performance, but using much less data. And indeed, we tried this. We said, let's reuse old trajectories that we have access to. Trajectories being a sequence of observations, actions, and rewards observed. And simply run the searches on those existing trajectories. Because for the tree search, it actually does not matter at all whether we are interacting with an active environment or whether we're just using some stored observations. It makes no difference to the search, since we're only using the learned model inside the search, but no interaction with the environment happens. And this means that for these old observations, we can generate new value and policy estimates that we can then use to train our network. And note here that we have now two different timescales in play. The trajectory was generated at some time t, whereas the new MCTS statistics were generated with a newer network at the time t prime. This is important for when we actually train the neural network from this data. For the policy, the case is still very easy. So let's split it to indicate the timelines. And then you can see for the policy, we can just distill the search statistics, the most recent ones we generated, and directly into the policy. For this policy loss, we do not care about the old trajectory at all. The policy is purely dependent on the current state. For the reward prediction, we have the opposite case. The reward only depends on the original trajectory. It does not depend on the reanalyzed searches at all, because we cannot change the environment interaction. Only for the value estimate are things a bit more complicated. Because we bootstrap for n steps, we have a mixture of the originally observed reward along the trajectory towards the value estimate in our newly reanalyzed data. So we actually have two different time steps here. And if you consider that now when we're training, we are the third time step, you can see that there are some certain off-policy issues here. The value estimate here in the search tree will be under a different policy than the originally observed rewards. And to simplify this issue a bit, instead of bootstrapping towards the average of the search, we can instead bootstrap to a target network. In this case, we only have two different timescales, the originally observed rewards and our new target network. In fact, this is what we used for our reanalyze Atari experiments. And in addition to using a target network, we also increased the replay by 10x. Replay meaning how many times do we sample training data inside our learner. And additionally, we used the reanalyze mechanism I just explained to generate 90% of search statistics, and only 10% were interactions with the real environment, generating fresh trajectories. And combining these two mechanisms, we could reduce our data consumptions by 100x, going from 20 billion to 2 million frames. This also fits very easily into the learning setup. As in a normal reinforcement learning setup, we might have some actors running our searches in this case, and some learner updating our learned model towards the trajectories. And they only communicate by sending network checkpoints in one way and episodes the other way. And so we can rearrange this picture a little bit. And now we can introduce the components necessary for reanalyze. First, we need a new kind of buffer, a reanalyze buffer, which can hold all the episodes that we generated by interacting with the environment. And we also need a second set of actors, the reanalyze actors, which can sample episodes from this reanalyze buffer, rerun the searches, and then send the searches to the learner. And for the learner, there's actually no difference at all between fresh episodes and reanalyzed episodes. They look exactly the same. This makes it very easy for us to vary the proportion between reanalyze and normal trajectories, and to simply enable or disable reanalyze completely. As you can see, this reanalyze mechanism is very effective in Atari. Using the standard budget of 200 million frames, we achieve very favorable results compared to previous algorithms. Finally, we performed a set of ablations to investigate the algorithm in a bit more detail and understand the contributions of its different components. We began in the game of Go to really nail down how much benefit we can get from search. This shows the playing strength on the y-axis of a fully trained network with a different amount of search time per move, comparing the real simulator to the learned model. And as you can see, both of them show strongly increasing playing strength with more search time. And astonishingly, the learned model can actually scale to 2 orders of magnitudes more search time than during training. It was trained at about 0.1 seconds per move. And the total improvement in playing strength is about 1000 ELO. This is also reflected in the size and the depth of the searches. We trained the learned model at 5 unroll steps, but during the search, it is actually unrolled several times as much. And as you can see, we still get very good performance out of it. We also did a sanity check in Atari to make sure that our good performance there was not due to, say, maybe the network architecture or our training setup. So we implemented a Q-learning loss to compare whether we could achieve similar results with this or whether we would not get as good results as with tree search. And indeed, you can see that the Q-learning achieved similar results to a previous R2D2 algorithm, versus MuZero with the tree search achieved much stronger performance. We also looked directly at the contribution of tree search, of Monte Carlo tree search in Atari and Pac-Man. In this figure, you can see different experiments trained at different numbers of simulations per move. And you can see as we increase the amount of search, the reward achieved over training and at the end of training increases. And astonishingly, actually, for me, even with only 6 or 7 simulations, which is fewer than the number of actions here, we can already achieve very strong performance. Still, we see further scaling as we increase the search. Finally, we also performed an ablation with sticky actions, which is a new proposed setting for Atari to ensure that algorithms don't explore and exploit any determinism in the environment. And in sticky actions, in 25% of the actions, actually the previous action is repeated instead of executing the one chosen by the agent. And as you can see, this does not affect the results from MuZero at all. It is very robust to these changes in the environment. You can also see in this figure, both lines actually represent 5 different runs, that the algorithm is very stable and very reproducibly achieves the same performance every time. So I hopefully have convinced you now why does MuZero work so well? Because of the search. Because the search is a very powerful policy and value improvement operator. It allows us to plan into the future. It gives us very good training signals that they are very similar to like supervised data you might have and less noisy than, for example, policy gradients could be. It's also easily scalable. You can just increase how much search you want to do, and you can get very stable training this way. Some possible extensions that you might want to investigate with the algorithm. Auxiliary losses, I think, are one approach that have been tried a lot in the literature. For example, reconstructing or predicting the observation. Given the transition function mapping to some state, we could try to reconstruct what is the observation that we would now be in. In our experiments, we could not get any benefit from this, but this may have been due to the large frame budgets we used at the time. I think it is possible that at smaller frame budgets, especially when going down to very small budgets like 2 million frames, that these losses may be more helpful, because then the reward data, the value data becomes very sparse. Another interesting extension would be to allow the planning to take advantage of multiple time horizons. Currently, the MuZero dynamics function is directly tied to the action sequences, but we might want to plan in longer jumps. We might to plan both immediately in the action sequence for the next few time steps and then in longer time steps. I mean, this is, for example, how humans might think about what to do next, right? Another possibility is to extend it to continuous action spaces. The domains we talked about in this talk, they're all discrete. In fact, there have already been some interesting papers about these extensions, both for AlphaGo and for MuZero. Finally, I would like to conclude my talk with a few tips if you want to reproduce this research or do some similar work. First, I'm of course conscious that for many students, resources are at a premium, so you would like to run your algorithm as efficiently as possible. For this, I would recommend the reanalyze, the 200 million frame setup from the paper. as is from the paper, it takes about 12 GPU days to train on one level. And the training cost there is primarily a function of how big is the network, how many flops, how big are the searches, how many simulations per move do we need, and on the training side, what's the replay factor, how many times do we train from each state, how many times do we train from each search, and how much do we train in general. How big is the batch and how many training batches, how many training steps do we train for. And these factors suggest some very straightforward ways of making this whole training much cheaper. We can reduce the planes of the convolutional network from 256 to 128, maybe even going lower than this. We can reduce the search from 50 to 25 simulations. As you saw in the figure before, this still achieves very good performance. And we can also cut down the length of our training runs. We can halve the batch size, or we can halve the number of training steps. And the combination of these measures should make it very feasible to train a full level in a few days, even on a single GPU. Finally, some more general advice. Most importantly, I think just try to visualize everything. This here is an example of our actor visualization dashboard, where we can see every currently ongoing game with statistics. Here, for example, a plot of the value and some general statistics about utilization and number of games played. And really, in our experience, visualization is the best way to find bugs. Neural networks are, fortunately or unfortunately, very good at doing the right thing in the wrong situation with the wrong input. So it can be very hard to find subtly incorrect network inputs. Profiling, of course, also if you want to squeeze the maximum performance out of your TPU, out of your GPU, they are standard profiling time tools that can show you where's the utilization, what are the bottlenecks. Even though I've talked a lot about reinforcement learning, I would actually advise to start with supervised learning, because this can be much easier to debug and it can be much easier to compare network architectures than reinforcement learning, because essentially you are fixing one part, you're fixing the data distribution, and you're only varying the network weights, the learning part. Maybe not as sexy, but testing also has caught a surprising number of issues in our code and saves us a lot of time, both testing individual components and making sure that the system as a whole works as intended, even if all the individual parts may be correct. And finally, don't repeat work if you don't have to do it. There are now a lot of great frameworks and components out there, from machine learning frameworks like TensorFlow, Torch. Personally, I'm a big fan of JAX, to environment implementations such as Atari and OpenSpiel. Once you have very good results, try to get as reliable as possible evaluations. Either if it's a game with 2 players, try to evaluate against known bots, or if it's a single player game like Atari, try to evaluate in all the standard conditions of the literature. Try to avoid making up your own metrics or your own evaluation conditions, as some papers sometimes do. Thank you for your attention. I hope this talk was useful to you.